In video 56 of Tensor Calculus, we're going to demonstrate what the cross product and curl look like in each of our sample coordinate systems. Now before we go to our individual coordinate systems, I want to reorganize this expression a little bit to make it easier to work with, and you're going to see an interesting pattern evolve. Okay, remember that our Levi-Civita symbols here are skew symmetric, so we only have to look at 6 terms. So we'll start first of all with epsilon 1, 2, 3, and j is 2, k is 3, so this would be A2, B3, and Z1. Alright, let's add to that the second term being epsilon 1, 3, 2, and here we've got A3, B2, and again Z1. Okay, now take a look at epsilon 1, 2, 3. What's it equal to? Well, by definition, it's equal to 1 over the square root of z times E1, 2, 3. And E1, 2, 3 is just equal to 1, so this is 1 over the square root of z. All right, epsilon 1, 3, 2 is just equal to negative epsilon 1, 2, 3, because we're just flipping the last two indexes here. So we already know what epsilon 1, 2, 3 is, so this is equal to negative 1 over the square root of z. So with that knowledge, we can rewrite our expression up here to be 1 over the square root of z times a 2, b3, and the second term becomes negative because of this action down here. The second expression will be a3, b2, and then we're factoring out the common term of z1. So this then is the expression for the first component of our cross product. Okay, let's look at the next one. This time we're going to look at epsilon 2, 3, 1, and its components would be j is 3, so A3 and B1 and Z2. Then we'll add epsilon 2, 1, 3, and we'll have A1 and B3 combined with Z2. Alright, same kind of drill as before. We look at epsilon 2, 3, 1. Well, if I flip the first two indexes, I'll get negative epsilon 3, 2, 1. And then if I flip the first and third, I'll get epsilon 1, 2, 3. And I have to flip the sign each time I do it. And of course, so what we're saying is that epsilon 2, 3, 1 is an even permutation. We already know what epsilon 1, 2, 3 is. That's just equal to 1 over square root of z. And then epsilon 2, 1, 3 is just the negative of epsilon 2, 3, 1. We just flipped the last two indexes. And since we already know this answer, then this one is equal to negative 1 over the square root of z. So we can now complete our expression up here, and it's going to be equal to 1 over the square root of z times a3 b1 minus, again, because of this term down here, minus a1 b3, and this time we're factoring out z2. Okay, one more to go. And this time we're going to have epsilon 3, 1, 2 times a1 b2 z3 plus epsilon 3, 2, 1 times a2 b1 z3. Okay, now epsilon 3, 1, 2 is equal to negative epsilon 1, 3, 2, flipping the first two indexes, and then it's equal to positive epsilon 1, 2, 3, because we're flipping the last two. And this, of course, again is equal to 1 over square root of z. I think you can see where this is going. Now, epsilon 3, 2, 1 is the negative of this one, negative epsilon 3, 1, 2, which means it's equal to negative 1 over the square root of z. All right, so this last term then becomes 1 over the square root of z times a1 b2 minus a2 b1 times our third basis vector z3. Okay, now notice that all of these results are extremely similar. They have exactly the same form. They all have this factor out front, and they all have a pair of terms subtracted from each other in the middle, and they all have a basis vector here. But the other thing I want you to see is that we can relate these by permutation. And what I mean by permutation is, let's draw it this way, 1, 2, 3, and I'm going to draw a little wheel like this, where we're permuting 1 to 2, 2 to 3, and 3 to 1. So notice how it works. I have 1, 2, 3. Well, if I rotate like this, 1 becomes 2, 2 becomes 3, and 3 becomes 1. I can actually derive the second term here from the first one there. Okay, do the same thing down here. 2 becomes 3, 3 becomes 1, and 1 becomes 2. So by simply writing down the first term up here, I can get the other two terms by inspection just by permuting the indexes the way you see here. So that means I only have to remember this expression. And that's easy. I have a basis vector here, z1, a2, and b3. The other term is just the reverse of the indexes. It's a and b, but the index is reversed with a negative sign. So I can do the cross product simply by inspection. I don't have to go through this exercise for each of our coordinate systems. Now, the next thing I want to show you is this. Here's our expression for the curl. You can look back in your notes or go back to video 53 to see where we derived this. Now, it's almost the same as the cross product. We have this factor, we've got the basis vector out here, and we've got the use of indexes j and k right here. So if we just substitute this expression for the product of a and b in the same, using the same index values, we'll come out with almost identical expressions here, except for the terms in the middle right here. Okay, so let's do it. What we're going to have for the first term is 1 over the square root of z times, let me just mark this off this way first. We'll have z1 as the first term, but now in this first term up here, j was 2, k was 3. So that would equate to this, the partial of a3 with respect to z2. And then the second half of this is just the inversion, a2 with respect to z3. And that's going to be the first component of the curl when we work it out. And then we can use the permutation technique I showed you here to find all of the other components. So what we have is a pattern that we could use as we go through each of our coordinate systems. You know, I think it was Lincoln who said if I had 4 hours to cut down a tree, I'd spend the first hour sharpening my axe. Well, that's kind of what we've done here. We've spent the time up front to do this analysis, and now you're going to see how quickly we can go through the individual examples. As usual, we'll start with Cartesian coordinates, and I'll begin by putting up the little pattern that we just got through deriving. So with this pattern, it's just a matter of writing down the answer by inspection. And we do it like this. First of all, the volume element for Cartesian coordinates is just 1, so there's nothing as a factor in front of each of these parentheses. But the first term, you'll see, is exactly this pattern. We have z1, A2, B3. Well, X is Z1, Y is 2, so A2 is A sub Y, and B3 is BZ. Once we have that, we can just find the others by permuting the results of this one. So 1 becomes 2, and then it's 3, 1. And the last permutation is 3, 1, 2, going around the little circle over here. And in each case, the negative term is just the term that you get by flipping the indexes. So we flip y and z as indexes here and here, and each term is formed the same way. Flip the indexes from the first term to the second, and we have the complete results. Okay, now the curl is equally easy. Again, there's no factor for the factor of 1 over the square root of z, because that's just 1. But we have 1, 2, 3 here. And we have 2, 3, 1, and 3, 1, 2. So we get all three terms just by permuting the indexes as we go around this circle. And again, the combining terms here are found just by flipping the indexes. Flip y and z to get this term, x and z to get this one, y and x to get that one. And those are the results then for Cartesian coordinates. It's just that easy. Okay, let's move on now to cylindrical polar coordinates this time. Once again, all we have to do is to follow the pattern. We can write the result down by inspection. Now for cylindrical polar coordinates, our volume element is rho, so that's why you see this factor out in front of each term. But this expression is identical to this, and the other terms are just permutations of this one. This has 1, 2, 3. Second term is 2, 3, 1. Third term is 3, 1, 2. Okay, writing down the curl is similarly very easy. You just write down the pattern and permute the indexes. Again, we have the volume element term, and the first permutation has indexes 1, 2, and 3. Then it's 2, 3, 1, and 3, 1, 2. So those are the results using the pattern. Okay, but for cylindrical polar coordinates, we also want to normalize the result. So what we have to do there is to make these substitutions. So how did I come up with all of these values? Well, we've seen our basis vectors before. We know that z1 is a unit vector, so it equates to rho hat. z3 is a unit vector, but z2 has a magnitude of rho, so we have to make this substitution because z2 is not a unit vector. But in past examples, we've been working with contravariant vector components, so this side's a little bit different. Now we're working with covariant vector components. So how do we figure this out? Well, these two are easy because if we're dealing with what are already basis vectors that are unit vectors, then these two simply equate. But what about this guy right here? Let's talk about it a minute. Well, to make that work, we know that we're looking for a result where A, the phi component of A times phi hat is equal to A2 times the contravariant basis vector 2. Well, basis vector 2 has a magnitude of 1 over rho. The covariant basis vector has a magnitude of rho, but this one has a magnitude of 1 over rho. So we can express it this way, A2 times 1 over rho times phi hat. Z2 equates to 1 over rho times phi hat. Well, that means that this guy has to equal this, or A2 has to equal rho times A. And so we have the same relationship for the B components as well. So if you take each of these values, substitute them wherever they occur here, then you'll find this result as the normalized result for the cross product in cylindrical polar coordinates. Now, I'm not going to bore you with the details of the substitution. That's all it is. You can substitute the values and you'll find that in every case the leading factor will cancel out. Okay, now we do the same thing for the curl, just make the same substitutions into this expression to get this for the normalized result. Now, the thing you have to be careful about in making substitutions in the curl is a case like this. When we substitute for A2 here, we make this substitution. Remember, we have to leave it inside the parentheses because where the partial differentiation with respect to rho is concerned, this factor of rho is not constant, so we can't cancel this out with the term in front. Now, other cases we can, such as right over here. When you substitute this in this place, rho is not dependent on z, so the factor of rho can come out and actually cancel this term. That's why the 1 over rho term only applies to the first term and has been removed right here. So as you make these substitutions, just make sure you're careful not to move any factors outside the differentiation if there's a dependency. Only do it if it's effectively a constant where the variable of differentiation is concerned. All right, if you do that carefully, these are the results then you're going to get for cylindrical polar coordinates. All right, let's move on next to look at spherical polar coordinates. Here we just go through the same drill. We use our pattern like this and simply write down the result. For spherical polar coordinates, our volume element is r squared sine theta. And then here we have our pattern, and it's permuted twice to complete the expression. Likewise, to write down the curl, we have our volume element term, our pattern, and it's permuted twice more here. Okay, all that's left then is to normalize the results, and to do that we have to make these substitutions. Now to get these values we go through the same kind of logic we did on cylindrical polar coordinates. For example, if we were looking at this expression, we'd want to equate A sub phi hat with A3 times the contravariant basis vector Z3, and because the magnitude of this basis vector is r sine theta, it's 1 over r sine theta, then we have to multiply that factor here to make it work. Okay, if you make these substitutions then for the cross product, this is what you're going to get. You'll find that making all the substitutions effectively causes all of these factors to die out. And then if you make the substitution for the curl, it looks like this. Now again, be careful as you do this that when you make the substitutions, you have to leave in any factors like this that are dependent on the variable you're using for differentiation. We can't cancel the sign here because the sign of theta is dependent on the differentiation. On the other hand, when we substituted here the value of r sine theta, the factor of r did come out of the differentiation. That's why we lost one factor of r over here. So just be careful at each step that you don't take any factors out that are not constants with respect to the differentiation. Okay, and there you have it for spherical polar coordinates. Now, I'm sure you noticed we skipped over affine coordinates and plane polar coordinates, and that's because our pattern only works for 3 dimensions. So for 2 dimensions, we have to go back and derive a new pattern. Well, here's our formula for the cross product in 2 dimensions, so we'll just write it out by hand. We have epsilon 1, 2 times a, let's see, j is 2 here, so a2 z1, and the next term would be epsilon 2, 1 times a1 and z2. All right, now these are the only 2 non-zero values for epsilon in 2 dimensions. Any other combination would have duplicates, so they'd be zeros. Okay, so we'll analyze it further this way. epsilon 1, 2 by definition in 2 dimensions is 1 over square root of z times e1, 2, again in 2 dimensions. And e1, 2 is equal to 1. So this is just equal to 1 over the square root of z. Then epsilon 2, 1 is equal to the negative of epsilon 1, 2, which is equal to negative 1 over the square root of z. So we can now complete our expression this way. This is equal to 1 over the square root of z times a2 z1, and this will be a negative term because of this, and it's going to be a1 times z2. And that is the complete expression for the cross product in 2 dimensions. So we can use this pattern for our remaining coordinate systems. For affine coordinates, all we need to do is to refer to our pattern for 2 dimensions and then substitute in the value for the volume element. And in affine coordinates, that volume element is AB sine alpha. So this is the correct expression for the cross product in affine coordinates. However, it's probably more useful to express the result using contravariant vector components instead of these covariant vector components like this, because the vector was probably expressed using contravariant components with covariant basis vectors. Okay, so to do that, we'd need to refer back then to our covariant metric tensor and simply write down the expressions we'd use for lowering the indexes. So we'd have a1 being equal to z11, which is a squared, times a1 with an upper index, plus z12, which is ab cosine alpha, times a2 in the upper position, and then a2 with a lower index is equal to z21, that's ab cosine alpha, times a1 in the upper position, plus z22, which is b squared, times a2 in the upper position. And having done that, we can now make those substitutions back into this expression over here. When we do that, the result looks like this. We've substituted this expression for a2 here, and this expression for a1 right here. All right, either of these forms works, but as I say, this one's probably more useful because the linear combination was probably formed with these components to begin with. Okay, and finally, we'll make mention of the fact that for the curl, it's simply not applicable because it is undefined in a system with 2 dimensions. So now let's finish up with plane polar coordinates. Again, all we need to do is to start with our model and replace the volume element, which for plane polar coordinates is simply r. So this factor becomes 1 over r, and this is the correct expression for the cross product. However, we do want to normalize it, and if we normalize it, we'd have to make these substitutions, and by now I'm sure you can see what we have to do to get these corresponding values. We simply substitute these back into this expression, and here's our result for the normalized cross product in plane polar coordinates. And finally, we again make note of the fact that the curl is undefined in any 2-dimensional system. So that's it for plane polar coordinates, and with that we are done. We have successfully demonstrated the cross product and the curl in each of our sample coordinate systems.